Hello viewers, welcome to another of our science lessons. My name is Buba Tamba, and today we will be looking at Newton's second law. In our previous lesson, we looked at forces, the effect of forces, and of course the definitions, what forces were, and we also looked at, we went as far as Newton's first law of motion. We looked at inertia in relation to bodies or objects, and today we want to look at Newton's second law of motion. How is change in velocity related to force? Newton's first law tells us that if there is an unbalanced net force acting on an object, it will move or change its velocity or result in an acceleration. But how does the net force accelerate an object? And what does inertia or mass actually have to do with it? When a cart with a hoop spring is pressed against a wall and released, the force of the spring will move the cart, obviously. For each of the questions below, make a note of how distance travel, speed, and acceleration change. How does the motion change as you change the compression of the spring? Try releasing the cart with about the same amount of compression, force without any added mass, then with the addition of 1 kilogram, 2 kilograms, 3 kilograms of mass. What happens to the motion? What happens to the motion? The answers, quick answers, of course. Compressing the spring exerts a force on the cart. Increasing the compression, obviously that is the force, increasing the force on the spring causes the cart to, 1, travel further in the same amount of time, have a higher average speed, accelerate more. Now, increasing the mass on the cart while keeping the compression force, that is the force, while keeping the force the same, causes the cart to travel a smaller distance in the same amount of time, also causes it to have a lower average speed and also a lower acceleration or a less acceleration. Now we look at questions. When the force acting on an object increases, the resulting acceleration will also increase, obviously, because we know that force is directly proportional to acceleration, right? So obviously if we increase the force on an object, obviously the acceleration of that object is also going to increase. Therefore, B would have been the right answer, right? When an object's mass increases, but the applied force stays the same, the resulting acceleration will A, remain constant, B, increase, and C, decrease. In this case, what do you think is going to happen? Obviously, the acceleration is going to decrease because acceleration is indirectly proportional to the mass, right? We can quickly do that here. We know that from F is equals to ma, therefore we know that A is equals to F all over m. And so there is a direct proportionality here. The relationship is inverse, right? So obviously if we increase the amount of mass of an object, the amount of mass of an object, obviously this is going to reduce, right? A is going to reduce, that is the acceleration. So therefore the resulting acceleration will reduce, right? Or will decrease, which is C, right? That is C, right? You are pushing a shopping cart so that it accelerates at 0.2 meters per second squared. You start filling the shopping cart with food. Do you need to change how you push on the cart for it to maintain the same acceleration? If so, in what way? A, no, you don't need to. B, yes, you push harder. And C, yes, you push softer. Obviously, you're going to take B. Why? Because now you are increasing the amount of mass, you're increasing the food content inside the shopping cart. So therefore, you need to increase the force so that it maintains that same acceleration. So therefore, B would have been the right answer. B would have been the right answer. Now we want to look at Newton's second law of motion. We are still under that actually. By performing the quick lab, you discovered Newton's second law. the acceleration of an object, right? A is directly proportional to or is dependent upon the net force acting upon the object. As the force applied to an object increases, the acceleration of the object also increases. That is true. Inversely, we are talking about the acceleration again. Still, the acceleration of an object is inversely proportional to the mass of the object. As the mass of the object increases, the acceleration of the object also decreases. So there is an inverse relationship. If you increase the mass, like we have here, if you increase the mass, the acceleration reduces. If you reduce the mass, the acceleration increases. If you increase the acceleration, the mass reduces. So there is an inverse relationship there, right? A more common way of writing Newton's second law would be, that is the summation F is equals to mass times acceleration, right? That is F net. In other cases, people will write F net equals to mass times acceleration. It's still the same. You can choose to write sigma F is equals to mass times acceleration. All the two are denoting is the total force, that is the net force, right? So it means the net force here and M here would mean the mass and A would mean the acceleration, right? Now Newton's second law identifies the relationship between acceleration and the net force. When a net force is applied to an object, the object accelerates. When a net force is applied to an object, obviously the object accelerates. If there is no net force, that means if the forces are cancelling out, obviously the object is not going to accelerate. But once there is a net force, the object will always accelerate. We already know that the unit for the unit of force is the unit of force in the SI or the metric system is the Newton. Also in the SI system, mass is measured in kilograms and acceleration is measured in meters per second squared. Therefore, the unit of force, the Newton, can be related to kilograms, meters and seconds using the second law, obviously. Of course, we can do that, as you can see. That is the summation here. So we denote this by its own unit. That is the SI unit for force is newtons. The SI unit for mass is kilograms and the SI unit for acceleration is meters per second squared. So this gives you the unit for mass. This gives you the unit for Newton, right? This gives you the unit for Newton. You will next be solving problems using Newton's second law. Remember how to solve a word problem and also how to solve for a variable. You always have to remember that, right? Okay. As in any game, there are few rules. Now, in our case, our rule number one will be to undo a mathematical operation, you must do the opposite. Like the opposite of addition, to undo an additional operation, obviously you have to do subtraction. That is the opposite of that. Division, the opposite is multiplication. So those are the opposites, right? 2, you can do anything you want except divide by 0 to one side of an equation, as long as you do the same thing to the other side. What you cannot do in maths is by dividing one side of an equation by 0 or by dividing anything by 0. So far, that is not acceptable in mathematics. But apart from that, whatever you do on the right hand side of an equation, you can equally, you are free, you are at liberty to do the same thing on the other side of the equation, and the equation will remain the same, right? If there is more than one operation going on, you must undo them in the opposite order in which you would do them. The opposite of the order of operations, right? You can always switch the left and right sides of an equation. Now let's look at the first question. A 3.5 kilogram object experiences an acceleration of 0.5 meters per second squared. What net force does the object experience? What net force does the object experience? Now, we want to solve this. What we do is, these are the options. A says 0.14 newtons, B says 1.75 newtons, and C says 3.5 newtons, D says 7 newtons. Which one is the right answer? Let's see. It says a 3.5 kilograms, right? That is our mass. So our summation F would be, right, M, A. Already we know what A is. A is 3.5. Already we know what our M is. M is 3.5 kg, and our A is 0.5 meters per second squared. 0.5 meters per second squared. .5 meters per second squared. 0.5 meters per second squared. So if we multiply the, if we do the maths here, what we eventually get is, this is division. So it's going to be 1.14 or something. I guess, yeah, 1.75. We will get 1.75. So if you do the mathematics, obviously what we get is, if you do, you will have 1.775 newtons. I better confirm this. So 3.5 times 0.5. So that's 1.75 newtons. So therefore, B would have been the right answer, right? In this case, B would have been the right answer. What force is required to accelerate a 1,000 kilogram sports car at 6.0 meters per second squared? Still the same, the net force. What you need is a net force is equals to MA, right? You're given the mass of the sports car as 1,000 kilograms times what is the acceleration required is 6.0 meters per second squared. Meters per second squared. So obviously this gives us something like 6,000 kilometers, 6,000 kilograms meters per second squared. Or this is what is called a newton. So you could also write it as 6,000 newtons. This would have been the right answer. So D would have been the right answer in this case. D would have been the right answer. A 12 Newton net force acts on a 36 kilogram object. What is its acceleration? Now we are looking for the acceleration, right? And the same thing, F net is equals to MA. Therefore, our A would be F net all that over M, right? That is what we are looking for. What is its acceleration? So F net is 12. So we say 12 divided by 36. 12 divided by 36. And that gives us 0.33. That gives us 0.33 meters per second squared. That's the acceleration. Meters per second squared. So this would have been the right answer, right? 0.33 meters per second squared. So A would have been the right answer. A boat strikes a 0.145 kilogram baseball. Oh, sorry, I'll take this again. A bat strikes 0.145 kilogram baseball with a force of 5,800 newtons. What acceleration does the baseball experience? What acceleration does the baseball experience? Still the same. Still the same. So acceleration will be the summation of F all that over M, right? And what is that? Is 5,800. 5,800 divided by 0.145. 5,800 divided by 0.145. So we have 40,000. So 40,000. So C would have been the right answer in this case. C would have been the right answer. An electric model train is accelerated at a rate of 8 meters per second squared by a 12 newtons force. What is the mass of the train? Again, the same thing. You are now looking for the mass, right? And the mass is, the mass would be F, summation of F all over the acceleration, right? We know what F is. F is 12 newtons. F is 12 newtons. Sorry. F is 12 newtons. F is 12 newtons. And We know what A is. A is 0.8. No. A is 8, not 0.8. A is 8 newtons, right? And so 12 divided by 8, we get 1.5. So we get 1.5 kilograms. That would be the mass. So B would have been the right answer in this case. An Olympic sprinter accelerates at a rate of 3 meters per second squared by applying a force of 245 newtons. What is the runner's mass? What is the runner's mass? Still the same logic. The mass of the runner would be F all over A, right? And what is our F? Our F is 245 newtons divided by, what is our A? Our A is 3 meters per second squared. 3 meters per second squared. 3 meters per second squared. So 245 divided by 3 meters per second squared. So we have 81 point something, which is around, 81.7. That's 81.7. So A would have been the right answer. A would have been the right answer. How much net force is required to accelerate a 0.5 kilogram toy car, initially at rest to a velocity of 2.4 meters per second in 6 seconds? So there is a hint for you here. It says use the definition of acceleration. What is the definition of acceleration? So acceleration is basically the rate of change of velocity with time, right? Acceleration is basically the rate of change of velocity with time. So what is the velocity here? The velocity is 2 point something meters, right? We know that V is equals to 2.4 meters per second, 2.4 meters per second, and the time here is 6 seconds. The time is 6 seconds. The time is 6 seconds. The time is 6 seconds, and therefore A would be V divided by T, and that is going to be 2.4 divided by 6. That would give us our acceleration. 2.4 divided by 6. We get 0.4 meters per second squared. Sorry. 2.4 meters per second squared. So this is our acceleration, right? Because why did we do this? It's because we needed this to be able to get the force that is required to keep this toy car in that motion, right? And so to get our initially how much net force, to get our force, basically what we will do now is to multiply the acceleration by the mass that we already have, that we were giving in the question. Now the acceleration is 2.4. The acceleration is 0.4, and so therefore our force, which is F net, is going to be 0.5 times 0.4. 0.5 times 0.4 times 0.5, which is 0.2. 0.2. Therefore, A would have been the right answer, 0.2. Now this one reads, a net force F accelerates a mass M with an acceleration A. If the same net force is applied to a mass 2M, then the acceleration will be, okay. It says a net force will be A, 4A, B, 2A, C, A over 2, and D, A over 4. Let's read the question again. A net force F accelerates a mass M with an acceleration A. If the same net force is applied to a mass 2M, then the acceleration will be, obviously, the acceleration will be reduced by half. Why? Because you have decided to double the mass. If you double the mass obviously the acceleration is going to reduce by half, because they are indirectly proportional. The mass is indirectly proportional to the acceleration. So if you increase this by 2, obviously you are reducing the other one by half, right? So that is therefore the right answer would have been A. The right answer would have been C, A over 2. A over 2. A net force F accelerates a mass m with an acceleration A. If F does not change, but the mass is half, the acceleration is going to double, like we did in the previous exercise. The acceleration is going to double. Why? Because you have decided to reduce the mass by half. So it's almost the same question, right? So the acceleration is going to double, right? 24. A constant net force acts on an object. The objects move with A, constant acceleration, B, constant speed, C, constant velocity, and D, increasing acceleration. So the right answer would have been A, constant acceleration. A constant net force acts on an object. The object moves with a constant acceleration, because that is what we said, right? If you apply a constant force, therefore the acceleration is also going to be constant. So the right answer for this particular question would have been A, right? Constant acceleration. The acceleration of an object is inversely proportional to A, the net force acting on it, that is acting on the object, B, its position, C, its velocity, and D, its mass. We have just explained that the acceleration of an object is inversely proportional to the mass of that particular object. So D would have been the right answer. So far, we have only calculated acceleration from a single force. Usually in real world, there are several forces acting simultaneously on an object. We did add multiple forces earlier on to obtain the net force. Thus, when using Newton's second law to solve for an acceleration, the mass, or an unknown force, we need to find the net force first. Yeah, so this was an example we treated earlier on, right? But then I decided to bring it so we could look at net forces and how we explain, a few things, right? And the acceleration. So if you want to get the net force here, which is your sigma F here, right, is actually going to be from the formula mass times acceleration, right? But in this case, we are already given the forces. So we can call them as F1 and F2. We can just include them in that manner. We can just, right? And so the acceleration now would be, as you can see here, the acceleration now would be F1 plus F2 all over m. What is F1? F1 is 20 newtons and F2 is 30 newtons. If you divide that by the mass, 5 kilograms, you get a certain answer. And what is that answer? Is 10 meters per second squared, right? So, and also to the right, the direction. Remember, it's a vector. Also to the right, the direction. Okay. So it says, this one reads, a force F1 equals to 50 newtons acts to the right on a 5.0 kilogram object. Another force on the object F2 equals to 30 newtons acts to the left. Find the acceleration of the object. So first, what we need to establish is our sign conventions. So to the right is positive and to the left is negative, right? So we would call this, let's say F1. Where is F1's direction? F1 acts to the right, so that is going to be positive 50 newtons, and F2 acts to the left, which is going to be minus 30 newtons. To the left is negative, that is the sign convention. To the left is negative. And so we know that acceleration is given as F1 plus F2 divided by m. Now what is our F1? Our F1 is 50 newtons, which is plus 50 newtons, and our F2 is minus 30 newtons, divided by our mass. What is our mass? Our mass is 5 kilograms. Our mass is 5 kilograms. So if you subtract 30 from 50, what you are left with is 20 20 divided by 5 gives you 4. 20 divided by 5. If you divide 20 by 5, all you get is 4 meters per second squared. 4 meters per second squared. So this would have been the acceleration. And this is going to be positive 4, because it's coming from here. So it's going to be positive 4 newtons per meters per second squared. So in this case, C would have been the right answer. C would have been the right answer. A force F1 equals to 350 newtons pushes upward on 20-gram object, on a 20-gram object, on a 20-kilogram object. Another force F2 equals to 450 newtons pushes down on the object. Find the acceleration of the object. Now upward is taken to be positive in the sine convention. So therefore our F1 is going to be 350 newtons, but then it's positive because it's going upwards. And our F2 is going to be 450 newtons, but it's negative because it's pointing downwards. It's going down. Find the acceleration, the same method. The acceleration now would be F1 plus F2 divided by m, which gives plus 350 minus 450 divided by 20. 350 minus 450. Okay, that's 100, and we divide that by 20, we get a 5. So we get a negative 5. This gives us minus 100 divided by 20, and the right answer would be minus 5 meters per second squared. Minus 5 meters per second squared. So therefore, B would have been the right answer. B. An object accelerates downwards at a rate of 5.0 meters per second squared. If the downward force on the object is 350 newtons and the upward force is 250 newtons, what is the mass of the object? What is the mass of the object? So the mass of the object would be F1 plus F2, all that over, sorry, I'm still on acceleration. Okay, so the mass of the object would be F1 plus F2 divided by the acceleration. Now let's look at this. What is our F1? Our F1 is 350 newtons, but then it is acting upwards. Is it upwards or downwards? Downwards. 350 newtons is acting downward. Therefore, it's going to be negative. It's going to be negative 350 plus our F2 is acting upwards, which is 250. 250. Divide that by 5 kg, 5 kilograms. Is it 5? Yeah, 5 meters per second squared. So 350 minus 250, that is negative 100 again. Negative 100 divided by 5, so that gives us negative 20 kilograms. Negative 20. Oh, but then in physics, you cannot write negative 20 because mass is not negative. It's not a negative. Mass is a scalar, so it does not really carry a sign. So the right answer would have been 20 kilograms. 20 kilograms. So this would have been 20 kilograms. Right? So now we will summarize Newton's second law, right, on this slide. So the acceleration of an object is directly proportional to the net force on the object. The acceleration of an object is directly proportional to the net force on the object. And also the acceleration is inversely proportional to the mass of the object. It's inversely proportional. They are inversely related, like we explained initially. And it's usually written as sigma f all over m. That is the acceleration. right? And the net force, usually we write that as sigma F equals to MA. So that brings us to the end of our today's lesson. I'll see you in the next video.